Assalamu alaikum everyone. This is Abdul Qadir Goni and I welcome you all in my IGCSE physics classroom. Today we are going to learn the chapter sound, chapter 13 of IGCSE 9th 1 physics syllabus. Okay, without wasting any time, let's get started. And before getting started, first have a look on the contents the chapter contains. First, we will be discussing about sound, what actually sound is, then the source of sound. After that, we'll explain how sound progresses through any medium. Then we'll be able to understand how to measure the speed of sound during any experiment. Then we'll study the reflection of sound, echo, sonar, refraction of sound, pitch and frequency, and we'll investigate the frequency of a sound using a CRO, that is the cathode ray oscilloscope. After that, we'll discuss about the audible range, the loudness of sound, the sound waves in different materials, how they travel and their speed, and finally, we'll solve some work examples from your book and will give you some idea how to solve the problems that will be faced in your IGCSE exam. So let's start. First, we are going to describe and explain what sound is. For IGCSE specification, you are supposed to write the definition of sound as sound is a longitudinal wave. Sound is a longitudinal wave, and sound is actually also a form of energy. There are lots of forms of energy like light waves, light energy, kinetic energy, thermal energy, gravitational potential energy, electrical energy. There are many forms of energies, and sound is also a form of energy. But in your exam, the answer of the sound wave will be a longitudinal wave. So the definition of sound is a longitudinal wave, and you must have learned the differences between transverse waves and longitudinal waves. There are two types of waves, transverse waves and longitudinal waves. And what is the major difference between these two waves? Transverse waves vibrates at right angles to the direction of propagation. For example, if the wave is traveling in this direction, in case of transverse wave, if the wave is traveling in this direction, then the vibration takes place at right angle to the direction of propagation. The direction in which the energy transfers, or the direction in which the wave travels, is called the direction of propagation also. So in case of transverse waves, the vibration takes at right angles to the direction of propagation. Or you can also write transverse wave vibrates at right angles to the direction of propagation, or a transverse wave vibrates at right angles to the direction in which energy is moving or the wave is traveling. And this is transverse waves. But for longitudinal waves, the vibration takes place along the direction of the propagation of the waves. For example, if the wave is traveling in this direction, the vibration takes place parallelly or along the direction of propagation. This is the direction of vibration and this is the direction of propagation. And in the transverse wave, this was the direction of vibration and this was the direction of propagation. Okay. So in case of longitudinal waves, the vibration takes place parallelly to the direction of propagation. For example, if this is the direction of propagation or the direction in which energy is traveling, in case of transverse wave, the vibration will be like this. The vibration is occurring at right angles to the direction of propagation. But in case of longitudinal waves like sound waves, the vibration takes place along the direction or parallel to the direction. Suppose the sound is traveling in this direction, the vibration is taking place in this direction. Okay, wave traveling in this direction, but vibration taking place parallel to the direction. If the sound is traveling in this direction, the vibration is also taking place parallel to the direction. This is the major difference between transverse waves and longitudinal waves. Okay, So sound is longitudinal waves. There are also other form of longitudinal waves like P waves and tsunami waves. Okay, and you can also produce a longitudinal wave in a slinky spring as well. Now, source of sound. Okay, what is the sources of sound? Any vibrating object is a source of sound. When something vibrates, it produces sound. So the source of sound is any vibrating object. If you drop a coin onto the floor, as long as the coin vibrates, you'll hear sound. When it stops vibrating, you'll hear no sound. So we can confirm that the vibration is producing sound. So any vibrating object can produce sound. Therefore, this is a marker and this is not vibrating actually, so no sound is heard. But when I strike the marker with another one, the marker will vibrate and this vibration will produce sound. So the source of sound is any vibrating object. Then progress of sound. Okay, we have learned what is sound and the source of sound. Now progress through medium, how sound waves travel through any medium. Before that, I'm gonna give you some idea about another classification of waves. Waves can also be classified or divided into two types: mechanical waves and electromagnetic waves. Electromagnetic waves like light waves, all the electromagnetic waves and cosmic waves, these waves are electromagnetic waves and they do not require any medium to travel through. For example, light comes from the sun or other luminous objects such as other stars from other stars to the earth, and there is space between the earth and other stars or the sun, no medium present there, but light still comes. It proves that light doesn't require any medium to travel through, and it also can travel through some sort of medium. For example, light waves can travel through transparent medium, for example glass, water, clear water, glycerin, plastic, but can't pass through wall. But other type of electromagnetic waves, they are also electromagnetic waves and they can also travel without medium, for example microwaves, radio waves, and they also can travel through some sort of opaque medium. The medium, those are not transparent. For example, microwaves can pass through wall and gamma rays can pass through almost everything. So the classification of waves in terms of requirement of medium are mechanical waves and electromagnetic waves. Mechanical waves require medium to travel through. For example, sound waves, water waves, these are mechanical waves, and these waves cannot travel without any medium. If there was no water, there would have been no water waves. If there was no medium, matter medium, for example air or solid or liquid, you can't hear sound. That means sound can't travel through vacuum. So sound wave is a mechanical wave and it requires a medium to travel through. Okay, and now we are going to explain how sound travels through a medium. And for example, I have taken air as a medium, and sound can also travel through actually solid, liquid, and any matter medium. And first, I'm going to explain how sound travels through air, and actually sound travels through other sort of medium, solid and liquid, in the same way. There is no difference between the way sound travels through any sort of medium. Okay, for example, this is a loudspeaker or speaker, and this is a paper cone, and I've just taken the paper cone for making you understand and making the diagram clearer and simplified. Okay, so this is the speaker and this is the speaker cone, and when you turn on the speaker or turn on any musical system, the speaker cone vibrates, and when the cone vibrates, you hear sound, and you can feel it when the speaker is producing sound, and if the cone is open or naked, and if there is no casing on the paper cone, and if you touch the paper cone, you'll feel it vibrating, and as long as it is vibrating, it is producing sound. So when the paper cone or speaker cone vibrates, it produces sound. Before the paper cone vibrates, okay, speaker cone not vibrating, consider these are air molecules. Okay, air molecules evenly distributed. Look at the diagram. Air molecules evenly distributed, and when the paper cone vibrates, it vibrates to and fro. That means from right to left, right and left. The paper cone vibrates to and fro. And before the paper cone vibrates, the air molecules are evenly distributed, evenly spread out. When the speaker is turned on, the speaker cone vibrates. For example, we are considering the speaker cone first starts vibrating to the right, then left. Okay, when the speaker cone is vibrating and when it moves to the right, when the speaker cone moves to the right, it will compress the air molecules. It will compress the air molecules closer to the speaker cone. Look at the diagram. When the paper cone moves to the right, it compresses the air molecules closer to it and produces a region of compression where the air molecules are compressed. Okay, and this region is called compression, the compressed region of air molecules. And this compressed air molecules then pushes against the neighboring air molecules. This compression will push against the neighboring air molecules, and so the compression will appear to be moving to the right. Okay, when the speaker moves to the right, it produces a compression here, and this compressed region of air molecules will push against their neighboring air molecules, so the compression will be appeared moving to the right. For example, this. And when it is vibrating, first it moves to the right, then moves to the left, and when the paper cone moves to the left, look at this diagram. When the paper cone moves to the left, it leaves behind a region of expanded air or a region of air molecules where the molecules are spread out or rarefacted. Okay, look at the diagram. When the paper cone now moves to the left, it leaves behind a region where the air molecules are further apart from each other, and we can say the region is expanded, so the air molecules get further apart, and this region is called rarefaction. Okay, this region is called rarefaction, and by this time the compression has moved to left because this compression has already pushed against the neighboring air molecules, so the compression appears to be moving to the right. Okay, and this is rarefaction, and the region where the air molecules are further away is called rarefaction, and the region where the air molecules are compressed is called compression. Okay, look at this diagram. The compression is appearing to be moving to the right, and after several vibrations, you'll see a series of compression and rarefaction moving from left to the right. Okay, look at the diagram. Compression, rarefaction, because after this compression, rarefaction, it will again move to the right and again producing other compression. By that time, this compression, rarefaction will move more to the right, and after several vibrations, this will produce a series of compression and rarefaction. So how sound travels through air? Sound travels through air by producing a series of compression and rarefaction. You have to write this on your paper if it requires. Okay, if you are to explain how sound travels through air, you will write sound travels through air by producing a series of compression and rarefaction. Compression, rarefaction. This is how sound travels through air. Actually, this is how sound travels through any sort of medium. I've explained how sound travels through air and sound travels through liquid or solid in the same way as shown or as explained. And same thing happens towards the right. When it vibrates, sound from the paper cone or speaker, the sound is traveling in direction, producing a series of compression and rarefaction, and also since it is moving left and right, it also pushes the air molecules closer to the left, so a series of compression and rarefaction will also be produced in this direction. Okay, in all directions the air is pushed, and therefore a series of compression and rarefaction will be produced, and this is how sound travels through air or any gas, any matter medium. We can say this is how sound travels through any sort of medium, whether it is air, whether it is any type of gas, whether it is a liquid, or whether it is a solid. I think you have got it. Okay, progress through medium. Now we are going to learn how to measure the speed of sound. Sorry, I have forgot to clear one more thing. If you were to label the wavelength of the sound, then you must label from the center of compression to the adjacent center of compression. Okay, from one center of compression to the next center of the, from center of one compression to the center of the adjacent compression is the wavelength. Or you can also label from center of one rarefaction, this is a region of rarefaction, this center, to the center of the adjacent or next rarefaction. Okay, and you can consider the compression or the center of compression as the crest, and the next center of the next compression will be the next crest, and we know crest to crest represents wavelength. And you can also consider the center of rarefaction as the throw, and throw to throw is again the wavelength. Okay, measuring the speed of sound, and I'll teach you 3 ways how the speed of sound can be measured during experiment. And first, I'm going to explain the simplest method, or the simplest of all the ways you can measure the speed of sound. And for this, you'll require a sound source that produces a loud sound, for example, 2 pieces of wood, and you'll require a companion. Ask a friend to help you. For example, you have asked your friend to stand in this position, and you are standing further a distance apart from him. It's your friend. Okay, it's your friend and it's you. And you have asked him to bang 2 pieces of wood together hard so that it produces a loud sound. Okay, and you will also require a stopwatch. Stopwatch. First, ask your friend to bang the 2 pieces of wood together, and start your stopwatch when you see him banging the piece of wood together. Okay, start the stopwatch when you just see him banging the piece of wood together, and stop the stopwatch when you hear the sound. And you have now the time taken for the sound wave to travel from this point, or from your friend to you, and measure the distance between your friend and you using a measuring tape or ruler or any other device or that can measure the length. And you have timed how long it takes to travel from your friend to you, and from the stopwatch you have t, and using the simplest equation of speed, v is equal to d by t, you can measure the speed of sound. This is the simplest method, but has lots of uncertainty there, because you have reaction time error, and for that the answer will be different from the actual value, the speed at which sound actually travels through air. but this is the simplest method. You can measure the speed of sound, and you can also use other sort of sound source that produces loud sound. For example, a gun, if you can afford. Okay, but two pieces of wood will be more available. This is the first method, and the second method is the measuring the speed of sound using echo. Okay, what is an echo? An echo actually is the reflected sound waves. For example, you are standing about 20 meter or 50 meter from a large wall or a building, or a distance that is about 50 to 70. Okay, the distance must be greater than 17 meter. Okay, suppose you are standing 50 meter from this is a wall, large wall, and you are standing here. Okay, and you shout as ma. Okay, you shout as ma. And when you just shout, you start the stopwatch, and the sound will travel in this direction and will be reflected from the wall and come to or returns to you. This is the ma reflected, or the sound reflected, and you will hear ma ma. Okay, and this is the reflected sound, and this is the echo of the original sound ma. So stand 50 meter or about 50 meter further from a large wall, a blank wall, or a tall building. Produce a sound by shouting, and start the stopwatch when you just shout. Start the stopwatch when you just shout, and stop the stopwatch when you hear the echo. And by this time, if by this time the sound has traveled twice the distance between you and the wall, because it has traveled 50 meter to this direction and again 50 meter to this direction. So the distance traveled is actually 50 into 2. Okay, and the time you have got from your stopwatch, because you have timed it, and using the formula V is equal to D by T. So D 50 into 2, and the time you have recorded by putting the value of time, you can measure the speed of sound. Okay, so a reflected sound wave is called an echo, and this method also has some sort of uncertainty, reaction time error, and to reduce the effect of reaction time error, you can do the experiment by increasing the time. Now, how you can increase the time? By standing further from the wall, but this this won't actually do more. So you can increase the time taken by producing several echoes. I'll be explaining this after this. Okay, and another thing, if you consider the distance between you and the reflecting surface, the wall is the reflecting surface here from where the sound is reflected. If you consider the distance between you and the wall as D, then the sound has traveled twice D. Okay, so if you consider the distance as D, the speed will be V is equal to twice D by T. But if you write the equation V is equal to D by T, you have to consider D is equal to 2 into 50. And in this case, 2 already taken and D is 50. You must remember these things. Okay, now to reduce the effect of the reaction time, what is actually about 0.1 second for average person, and stand here and ask your friend with 2 pieces of wood together just beside you. Okay, you and your friend, you both are are at the same distance from the wall. And suppose your friend, and you have asked your friend to take two pieces of wood together. First, ask him to bang and start the stopwatch when you hear the sound, because he or she is standing right beside you. Therefore, when he or she just produces the sound, you will hear it. Okay, when he bangs two pieces of wood together, start the stopwatch and wait for the echo to return. When suppose you have produced a sound ma, and you and your friend both are standing 50 meters from a large wall, okay, when the echo arrives, it will travel 15 to 200 meters, and don't stop the stopwatch. Okay, when you hear the first echo, your friend will produce another sound, or your friend will bang two pieces of wood together. So the second sound will travel 50 meters, and again 50 meters. You'll hear the echo. Still don't stop the stopwatch. Repeat it for 20 claps or 20 times. Okay, they are repeated for 20 times, and by this time the sound will travel 20 into 2 into 50. Okay, and you have recorded the time for 20 claps, so V will be this distance divided by the time you have recorded. Okay, so I'm again repeating it. First, ask your friend to, or first, before starting the experiment, you will inform him or her to produce 20 sounds, and we'll wait for 20 echoes, and the sound waves must be produced in a rhythm. For example, you have produced a sound, or your friend have produced a sound ma, the echo comes, the echo ma, then again bang two pieces of wood together, wait for the next echo, then again bang the piece of wood together, wait for the echo, and do this 20 times, and start the stopwatch when he or she first bang two pieces of wood together, and stop the stopwatch when you hear the 20th echo. And doing this, you have time for the sound to travel for 20 into 2 into 50 meters. Okay, so what will you write in exam? Ask your friend to bang two pieces of wood together, start the stopwatch, hear the echo, and he or she will again bang two pieces of wood together in a rhythm. So you produce one sound, you hear the echo, again produce one sound, hear the echo, and in this rhythm you produce 20 sounds, and you'll hear 20 echoes, and you start the stopwatch when he or she first produces the sound, and stop the stopwatch when the 20th echo is heard. And by this time the sound will travel 20 into 2 into 50 meters, and the time recorded will be t, and using the equation v is equal to d by t, you will be able to measure the speed of sound more accurately, having less reaction time error and less percentage uncertainty. Reflection of sound. Like any other wave, sound waves can also be reflected, and we know that from the properties of waves, all type of waves can be reflected, okay, and refracted also. So sound waves can also be reflected. For example, this is a large wall, this is a pipe, and if you have a sound source, for example a ticker clock here, place another pipe, and here from this position you will be able to hear the sound. Okay, the sound is traveling in this direction, being reflected from the surface. It changes direction and reaches your ear. Okay, so and for like other waves, in this case the angle of incidence is also equal to the angle of reflection. This is the law of reflection, you know. Now echo, we have already explained about it. Echo, the reflected sound wave, is called an echo. Sonar. Sonar. What is sonar? Sonar stands for sound navigation and ranging. Sound navigation and ranging. And using this method, actually the ship measures the depth of the seabed beneath it. And now I'm going to explain how a ship can measure the depth of the sea beneath it. For example, this is a ship. This is the seabed. Here it will have an equipment that produces sound and also receives the echo or the sound that is reflected from the seabed. Okay, suppose this is the H, the depth of the sea. Okay, the equipment produces sound and receives the sound that is reflected from the seabed. Okay, and the machine automatically times how long it takes for the sound wave to travel back to the sensor after it has been produced. Okay, it has timed, or it will time the time taken, or it will record the time taken for the sound to travel back or to return back to the equipment after being reflected from the seabed. And using the simplest equation, V is equal to d by t, you can find out the depth of the sea if you know the speed of sound v. Okay, and in this case the speed of sound is known, and in water the speed of sound is about 1500 meters per second, and it varies with density and temperature. Okay, and if you consider the depth as h, the distance travel is actually 2 into h. Okay, twice h, because the sound has traveled h distance, and for coming back it has again traveled h again. Therefore the distance traveled by the sound wave is twice h, and v is known, so making h as subject, you can measure the depth of the sea beneath the ship. Okay, and if you don't like to use this formula, simply use this, v is equal to d by t, and this is the d, and in this case d is the distance traveled by the sound, and it has traveled twice the distance or twice the depth of the sea. Therefore after finding d, v into t, after finding d, you have to divide it again by 2 to find the depth. Okay, and if you use this formula with the twice h by t, you'll directly find depth h. Now refraction of sound, like other waves, sound wave can also be refracted. It changes direction when its speed changes, and the speed of sound depends on the density of the medium. If the density of the medium varies, the speed of sound also varies. It also changes with temperature. Now if the speed of sound increases with increase in temperature, and for 1 degree Celsius increase in temperature, the speed of sound increases by 0.6 meter per second. For 1 degree Celsius increase in temperature, the speed of sound increases by 0.6 meter per second. And in air, the speed is typically at room, the temperature, normal temperature, room temperature is about 340 meter per second. Okay. And with change in temperature, the speed varies and also varies with the density of the medium. And if you have the right condition, you can demonstrate the refraction of sound. But since sound cannot be seen, but can be heard, using your hearing skill, you can observe or investigate the refraction of sound. Suppose this is a pond. Okay. This is a pond, and one of your friends from this part of the pond calls you by your name, and you are standing on the other part of the pond, and you'll hear the sound much louder and clearer than it would actually be. Okay, why? As you go up, the density of the air falls because of the temperature condition, and since the air molecules closer to the water surface is actually cooler than the air above, therefore the density at the lower part of the atmosphere will be higher, and if you go up, the density falls. Okay, so when you produce the sound, suppose your name is Jack. Okay, sorry, I have drawn a girl. So suppose your name is Rose, and he calls you by your name Rose. The sound directly reaches you, and you hear the sound Rose, and this is the direct route or direct path the sound takes, and the sound also travels in this direction also. But when it is traveling in this direction, due to change in the density, the speed of sound varies. And in the light waves chapter, we know that when a wave travels from a more dense to a less dense, okay, so when this is glass, suppose this is air, this is more dense, this is less dense, and when a wave travels from a more dense to a less dense, it bends away from the normal. Same thing happens here. When this sound is traveling in this direction, the density of the air falls, therefore it is traveling from a more dense to a less dense medium, therefore its speed changes and it bends away from the normal, and it is refracted. And again it is refracted, and by several refraction it will reaches you later. Okay, first you have heard Rose, and you'll heard Rose, another sound that has been refracted and reaches you. Therefore the sound Rose you heard will be louder and clear. Okay, pitch and frequency. Pitch, the word pitch refers to the frequency of a sound. For example, suppose you have a violin. The string of violin is small and it vibrates faster, and small objects vibrate faster, and the sound produced by small objects are heard as notes of high pitch. So the sound, the word pitch, sorry,